Hey, welcome. This is a MathRep that you just encountered. And so if you're watching this, that means that you are most likely here to figure out what the heck was that and how do I deal with it. Okay. So we're going to go through each of the components, try to do so quickly and effectively, and give you an opportunity to make sense of this. I also thought it'd be helpful to record this instead of doing this in person as a way to allow you to go back and scrub and to uh, check the video out multiple times without the pressure of class time and that kind of thing. So we're going to be referring to f of x, which is this green graph that you see here, and we're going to answer each of the questions that are on this document, this MathRep, with respect to that green curve. Okay, so the very first one, explain why f represents the graph of a function. Well, if we draw a vertical line at any point along this trajectory of this curve, we notice that the intersection of that vertical line, or with any of the vertical lines, intersects the graph, the green graph, at most one time. And so by the vertical line test, we know f of x is a function. One way to think about that is you may notice that for each x input, you get a distinct y value. However, there are several y values that are repeated uh, for individual x values. But what's important is that for every y value, you get you're not having repetitions of those x values. So for example, um, a better way of saying that would be for each x value, you're getting a unique y value or one y value. You're not getting multiple y values. In other words, you're not getting a y value here for this value and then another y value down here or something like that. So you're getting just one output from the input. And so even though multiple inputs correspond to the same output value, the input is only getting one output. Okay. So that is what the definition of a function is, and that's what we're looking for here. All right, let's knock some of these off. Okay, so the domain. So if it doesn't explicitly state it, but you can imagine what's happening here in the graph being cut off is that this graph is just going to continue in both the positive and negative x directions for infinity, and every value along that domain is completely defined. So the domain is actually from negative infinity less than x less than positive infinity, or another way of saying that is all real numbers. Okay. Now the range is very similar. However, do you notice that if we draw horizontal lines going this way, there is a value at which my horizontal line no longer intersects the green curve. In other words, like for example, y equals 4, the horizontal line y equals 4 does not intersect the curve. And so the range actually stops at a certain point. And we got to kind of figure out what that value is here. And so if we were kind of just guessing based on the values here, it looks like the spacing between each of these numbers is 1. So 1, 2, 3, 4. So it looks, if I'm just kind of eyeballing it, that the y value here, where the function is last defined, is at y equals 3. And so it looks like, not sure 100% because we don't know explicitly the equation of this graph yet, but it looks like y equals 3 is the largest y value. And then the smallest y value, well, again, these are going off to negative infinity. So any value down here is going to be in the range, but the values greater than y equals 3 are not in the range. So the range is everything for y uh, less than or equal to positive 3. Okay. So the domain again, or you can say that it's from negative infinity less than or equal, not less than or equal to, just less than or equal to 3. So both of these are okay. This implies that, just to be a little bit more explicit. Um, and again, the 3, we don't know for sure if that's the actual value of it. That was just estimating it, but it does look like that is the case. All right, let's look here. So the x-intercepts are these specific values that cross where our curve, our green curve, intersects the x-axis. And so it looks like it's at -1 and 1. and I drew over that. Oh, you know what? That can't be one because one's right there, it looks like. So this is going to be halfway between those. So this looks like it might be 1.5, and this looks like it might be -1. So our x-intercepts then are going to be at x equals -1 and x equals -1.5. You may notice that the y value here is 0. So you can also write these as ordered pairs, -1 comma 0 and -1.5 comma 0. Both are acceptable answers for this particular problem. The ordered pairing, the x value and the y value together, because again, this is along y equals 0 here. This is the x-axis. That is probably a better answer because these are points. The y-intercept is exactly the same thing as the x-intercept, except for along the y-axis here. And so it's at that location right there. And that's an estimate between two, that's so 3 is right there. So it's going to be a little bit less than 3. Um, so without an exact value, y is going to equal, um, hmm, if I look closely at it, it might be, actually, this might be a little bit higher than 3, because that does look like it's right at 3. So maybe this is y is less than like or equal to like maybe like 3/2, 3.5. Maybe that's the value there. Maybe it's a little bit higher because it looks like this is right at 3. Looking at it a little bit closely. So let's just say that it is. So we're gonna just change this again. We'll figure this out for sure, but I just want to pull out where this is coming from. So I'm eyeballing it. I thought it looked like maybe it was 3. Maybe it's like 3.5. Maybe it's a little bit higher because it does look like the y-intercept is right there at 3, and then it's still going up, and then it stops kind of climbing right there. So, which does bring me to the intervals of increasing. Okay, so one way to think about this is if you have your little guy kind of walking along this curve, if you can imagine him kind of cruising along this curve and then coming back down, at what values or where is he walking up a hill? That would be the levels or the intervals of increasing. So it looks like he's going up the hill till somewhere right around here. That looks like where he kind of reaches the top, and that looks like it might be right in between was that a half and a 0? So what's halfway in between 0 and a half? Well, it'd be 0.25, right? Uh, so the intervals of increasing look like it's going to go from -infinity less than x less than or equal to 0.25 or a quarter of the values. It looks like he's climbing up there, and then he stops, and then he starts climbing back down. And so the intervals of decreasing would then be from 0.25 less than or equal to x less than infinity. Again, this is going to continue off to infinity forever. That's the intervals of increasing. So where are you climbing up? Where do you stop? And then where do you climb back down? So that would be the intervals of increasing and decreasing. All right. Understanding the evaluation. So find f of 0. So f of 0, if we plug that in, that would be the y, that would be exactly the y-intercept. And so we already found that. So this would be y equals 0. Sorry, not y equals 0, y equals 3. That is when x is equal to 0. So that's the y-intercept. And then is f of x odd or even or neither? Well, this looks like it's an x squared. It could be an x to the 4th. It could be an x to the 6th. We don't know. But if it is any of those, that wouldn't matter because for this question, because that would mean that this question would be even. So this is an even polynomial. And then the domain and range, well, we kind of already covered that here individually with that up there. So the domain explicitly would be then from -infinity to +infinity in interval notation. And the range would be from -infinity up to that value of, I think we're going to call it 3.5 now. And it is inclusive there. So we would have a bracket there because it would include that value as part of its range. Okay. And then what else do we have left on this? Over here, it says, does f of x have an extremum? Well, what is that word extremum? Extremum means, does it have a maximum or a minimum or a highest value or a lowest value? Okay, so this is it's either like a highest point if it's if it's a max or the lowest point, um, if it's a min. Okay, and so there are, for example, functions that have local, meaning close by, like highest mountains. So if you think about maybe like the foothills around here, around the valley here, um, if this is Fresno, okay, then as you kind of come out here, you have some hills here heading out to up to like Kings Canyon or Yosemite National Park. Right, you have some. So each of these mountains would be a local maximum. That's a local high point, uh, and then the valleys would be local minimum. But not only, but when you get all the way over here to Mount Whitney, that would be a sort of global maximum or highest point if you considered all of, like, let's say California or the lower 48 states. Okay. So that's the idea of an extremum. And so we just got to look at our graph here, and do we see a point where this graph kind of reaches a highest or a lowest point? And as my little guy was showing, it does kind of look like he gets to a highest point here at that value of x equals 0.25. And so we would say, yes, this has a max at x equals maybe 0.25, and its value. Okay, so the x coordinate is where it occurs, and the y coordinate is where how much of it is. In other words, like how high elevation wise are you? And I think we were kind of saying that that might be like 3.5, maybe. So maybe like 3.5 units, maybe like it's feet or kilometers or meters or miles or something like that. And so, what is the sign of the leading coefficient, and how do you know? Well, that part requires a little bit of knowledge about this thing. And so, noticing that this goes this way, right? It's opening, if you want to call it opening down, and it looks like it's a mountain, right? So it's opening down. Uh, and if that's the case, then our leading coefficient determines which direction our polynomial opens. And so let's just pretend that this is ax squared plus bx plus c. It's something of this form. The a term here is the leading coefficient. And so if a is negative, that means that when x gets really, really large, remember x is always positive here, x squared is always positive, I should say, that in order to make this thing open down like this, a would have to be negative in order to make it go downwards. In other words, these are negative y values. And that's the only way then that this function would be negative as x gets really, really large. And so that means that a has to be less than 0, or a is negative. Okay. And how do we know? Well, we know that because when x gets really, really large, the only way, again, to make that to make a positive number turn into a negative number is if you multiply it by a negative value. So a has to be negative. If it had been opening up, then it would be positive, because you get a positive number times a positive number makes that positive. All right. And then what is the value of the discriminant? Is it positive, negative, or 0? Well, if you remember the quadratic formula, x equals negative b plus or minus b squared minus 4ac all over 2a. If you remember that, or if it brings back some vague tigglings of your brain, the quadratic formula has within it, underneath this radical here, that b squared minus 4ac. That's what is called the discriminant. Okay, and so if it's positive, right? If it's positive, that means that b squared is bigger than 4 times ac. So if b squared is greater than 4ac, that means it's positive. That b squared is positive because it's a bigger number, you're subtracting off a smaller number. If it's less than 4ac, that means that this b squared is smaller than 4ac, and so when you subtract a bigger number from a smaller number, you get a negative value. And if it's equal to 0, that means that b squared equals 4ac. Okay. In this case, how does that look like graphically? I don't need to calculate anything. I can actually find it directly from the graph. If it's equal to 0, that means I would have exactly one x-intercept, but I don't. I have two. And so since that's the case, since I have two x-intercepts, that means that I know that the discriminant is greater than 0. Okay. so it's actually positive. It's actually positive. It's strictly greater than zero. Again, because that gives me, it's the only way that I can get a real number out of the square root here, which would then give me the two radicals there. Okay. All right. So that's the explanation of each of these pieces in total. I hope that was helpful, and I look forward to seeing you tackle this with more success in the next round. Good luck.